Hello viewers, I am Rajalakshmi. In today's session, we are going to see about scalar time. What is the definition of scalar time and what are the basic properties of scalar time? What is scalar time? Who proposed scalar time? Actually, the scalar time representation was proposed by Lamport as an attempt to totally order events in a distributed system. In scalar time, the time domain is a set of non-negative integers. For example, let's assume Ci is the timestamp of the process Pi, then Ci is an integer number and also it is the local clock of the process Pi and its local view of the global time. Now let's see about the rules. We know very well that the first rule R1 governs how the logical clock is updated by a process when it executes an event. So, before executing an event, whatever the event, send event or receive or internal event, okay. So, before executing any event, the process Pi executes the following statement. What is the statement? Ci is equal to Ci plus D, where D is greater than 0. Timestamp of the process Pi is incremented by D. The value of D will be usually 1. In general, every time R1 is executed, D can have a different value and this value may be application dependent. However, typically D is kept at 1 because this is able to identify the time of each event uniquely at a process while keeping the rate of increase of D to its lowest level. Now let's see about the second rule. What is second rule? This rule governs how a process updates its global logical clock to update its view of the global time and global progress. So here each message piggybacks the value of its sender at sending time. When a process Pi receives a message with a timestamp C message, it executes the following actions. The first action is it selects the maximum among Ci and C message. Then it executes R1. What is R1? R1 is going to increment the value of Ci by D. Okay. So that rule is executed here. And then the message is delivered. Now let's see an example. Here, 3 timelines are available. The first timeline, it represents the progress of process P1. Second line, it represents progress of the process P2. And third line is for the third process. In the first process, totally 5 number of events are happening and P2 is containing 6 number of events and P3 is containing 4 number of events. Before executing any event, the clock is incremented by 1. So, this is the first event of the first process. So, before executing the first event, the clock is incremented by 1. Okay. Then the first event is complete. Now, after some time, the second event is going to be executed in process P1. So, before executing the second event, the current clock value is incremented by 1. So, now the timestamp of this event becomes 2. Now, it is a message passing event. So, this event is passing message to the second process. As we know already, this message piggybacks the time. Now, in the second process, before executing the first event in the second process, its logical time is incremented by 1. Now, the timestamp of the first event available in the second process is 1. Now, the second event is going to receive message from the first process. So, now the rule 2 is applied here. Now, the timestamp of the process P2 is compared with the timestamp which is available in the message. And it is identifying the maximum among those two values. 2 is the maximum value. Now, Ci is assigned with 2 and then Ci is incremented by 1. Now, it becomes 3. So the timestamp of the second event which is available in the second process is 3. So in this way, all the timestamps are incremented. All events are getting the timestamps. So, according to this particular diagram, the process 10, that is the process which is available here, this process with the timestamp 10, which is available in the second process, will have knowledge about all the processes that are available, that are happening in the 3 processes P1, P2 and P3. Similarly, the process with the timestamp 11 in process P2 or event with the timestamp 11 in process P2 has all the knowledge about all the processes or all the events that are happening in all the processes. Now, here this B is there, no? So this event with the name B is containing the timestamp 6. Now let's see the basic properties of scalar time. The very first property is consistency property. Scalar clocks satisfy the consistency property. For example, for two events EI and EJ, EI implies EJ. It implies that timestamp of EI is less than timestamp of EJ. Here EI and EJ represents the events. Okay, so if EI is happening before EJ, it implies that timestamp of EI will be less than timestamp of EJ. If this condition is satisfied, then we can say that the consistency property is satisfied. So scalar time is satisfying the consistency property. The second property is total ordering. Scalar clocks can be used to totally order events in a distributed system. Main problem in totally ordering events is that two or more events at different processes may have identical timestamp. A tie-breaking mechanism is needed to order such events. A tie broken as follows. Process identifiers are linearly ordered and tie among events is broken on the basis of their process identifiers. The lower the process identifier in the ranking, the higher the priority. Now, the next property is even counting. If the increment value d is always 1, the scalar time has the following property. If event E has a timestamp h, then h minus 1 represents the minimum logical duration counted in units of events required before producing the event E. It is the height of the event E, that is h minus 1 events have been produced sequentially before the event E. The next property is no strong consistency. The system of scalar clocks is not strongly consistent. That is, for two events EI and EJ, if timestamp of EI is less than timestamp of EJ, it does not imply that EI happens before EJ. With this, we are completing today's session. Thank you.